Please give a warm welcome to Dr. Eugene Tu. Go ahead and take it away.
All right. Hello, everyone. Thanks for taking the time. And it's my pleasure and honor to come and talk to all of you. I don't know how many of you know that I live here in Fremont, just up near Mission San Jose area. I've been here, I guess, now, trying to go back and think, probably about 15, 16 years. And my three kids have all gone through school here. My oldest son has just graduated from UC Santa Cruz, is just doing his master's work. My middle one is at UC Santa Barbara right now, and my youngest, Elena, is at Mission San Jose High School in 10th grade. So really, it's home here, and it's a pleasure to talk to all of you. I've had great opportunities to talk to many of the high schools here. I think most recently, I think it was American High School that hosted an event that I had an opportunity to talk at. So I'm really here to just chat with you, answer questions, I can talk a little bit about my background and how I got to where I am, and just see where the conversation goes and what you might be interested in. And so let me start though with, I'll share some slides that might just inspire some questions or areas that you might be interested in talking more about. I know there were some questions that were presented up front on the registration form. I've got a list of those, so we can also talk about those, but we can take this however you'd like. So let me try to share the screen here, and somebody can just confirm that it's working and you can see the screen. All right, great. So again, I'm Eugene, and I'm the Center Director at Ames Research Center. If you don't know where it is, it's located pretty much at the junction of Highway 101 and 237, right near Mountain View, Sunnyvale. If you ever see the huge hangar, it's actually not covered right now. You just see the structure of the hangar. That's kind of right where it is. There's an airfield there as well, and I'll talk a little bit more about that. Let me start with a little bit of background. I know there are a lot of questions that usually come up when I talk to students about how did I get interested in this field, and was I interested early on? The answer is yes, I was. And let me just see, I need to advance the slide here. So this was my hobby when I was a kid growing up. I loved model airplanes. I built them and I flew them. We didn't have the same type of computers that are available nowadays, and video games and other ways. So you had to go outside and really build things and play with them that way. So that's what I did. Personal computers just started to come into being when I was in high school, and then of course into college. And so of course, I did get very much into computers later on, but in the early days, it was all about sort of the hobbies and the model building and such. I did end up going to school pretty close by. I went to Cal, and I did originally apply to go both there and up to University of Washington and some of the other schools on the West Coast. I ended up at Berkeley, and at that time, I was in letters and science, so I wasn't actually in engineering at the beginning. I wasn't 100% sure that I wanted to do engineering, even though I enjoyed it. So I was in what was called an undeclared major. And I don't know if that still exists, but at that time, you could apply to undeclared, and you would go into the College of Letters and Science, and then after a year or two, you could declare your major. But it became pretty early on a strong interest of me in continuing my interest in engineering. I took math courses in my freshman year. I took physics. I took chemistry. All the courses that you would need to do for engineering, even though I wasn't officially declared an engineering major. And a lot of times the schools will say, and they said back in the days when I was there, which was in the early 80s, that it's really hard to get into engineering. You don't want to apply to a school in a different major and then try to transfer over to engineering. I think that's partially true, but that's not 100% true. If you do well in college, if you do well in your early classes, you will be able to transfer to almost any degree you want to. Once you've proven that you can handle the coursework, handle the load, and do well. So don't think that whatever you've applied to or whatever major you've gotten into a university in is the one you have to stick with. If you change your interest or other things become more interesting to you, or your passion takes you elsewhere, you can change majors and even colleges within a university, or even transfer. People do transfer schools too, or transfer universities. So just keep that in mind. But for me, I came into UC Berkeley in letters and science, and then as an undeclared major. And then after my first year, I knew that I wanted to do engineering, so I went ahead and applied and got transferred into mechanical engineering at that time. I was there. The image there on the far left is of the Kennedy Space Center, the vehicle assembly building. So very early on, I had a chance to go visit there. And the image on the upper right is the big game. So I was actually there during what they call the play, which was when Cal beat Stanford on the very last 4 seconds of the game. And it's probably one of the most famous big games in history. But the key thing is I did decide at that time to do an internship. And I didn't do a high school internship, but I did do a college internship. So after my second year, I had an opportunity to volunteer and do an internship at NASA Ames. And so that's what I ended up doing. And so I basically volunteered for about 6 months over the summertime, and even during school, since Ames was only about a 45-minute drive from Berkeley. I would go there once a week and just volunteer, work with researchers, do whatever they needed done. At that time, it was probably things like copy machines and cutting and pasting, literally cutting and pasting with scissors and tape, figures and things that you would put into papers that would end up being your publication. So we didn't have all the cool graphics on computers at that time to do that. You basically have to type up papers and cut and paste them in. But I would do whatever it took to learn about the area and to have mentors who were in the field. And so that's what I ended up doing. When I graduated, they offered me a position at Ames. And more importantly, they offered me the opportunity to continue my graduate studies. So NASA offered to not only hire me, but say, hey, we'll pay for you to go on and get your graduate degrees if that's what you're interested in doing. And that was what I was interested in doing. I was either going to go on to graduate school and just get my master's and eventually my PhD on my own, or I could be paid to do it and work at the same time, which is what I chose to do. So I did end up doing that. And one of the things I got to do while I was at NASA is in working with some senior researchers, like the folks shown in the picture here, I was able to publish papers, even as a first author, but sometimes as a second or third author. I would be able to write papers, publish them in conferences or publish them in journals, which really also helped me prepare for the rigors of graduate school, because that was the path I was on, was to continue to do research, even though, as you see now, I didn't end up there. So I did go to graduate school, and Stanford was where I ended up going, even though I'm still remain a big Cal fan. And so there's, of course, a rivalry there in sports. But I did end up going to Stanford, ended up spending more time at Stanford than Berkeley, because it took me a little bit longer. It took me 7 years to finish my PhD, because I was working at the same time. But the positives of that was I was actually applying what I was learning in the work environment. And I was able to actually, the research I was doing at work was mainly part of my PhD dissertation. So I was able to combine both of those. And so it took me a little longer, but it was well worth it. And I certainly enjoyed that. I thought you might find this one to be interesting because Cal and Stanford are such rivals. When I became center director, 2 astronauts who knew me, one went to Stanford, one went to Berkeley. They actually flew together on one of the space shuttle missions. So this is actually a picture taken on the space shuttle where they each brought a flag of Cal and Stanford up there. And it says there that we can coexist peacefully in space. So I just thought that was a cool image from my background. So let's talk a little bit about what NASA does. And so what you have here is a lot of times people think of NASA, they think of space exploration, they think of the International Space Station, they think of the space shuttle. You might think about the landings on the moon from Apollo 50 years ago. But NASA is actually much more than that. And so these are the 6 areas of NASA. So just wanted to highlight that for you. On the upper left, Earth science is one of the biggest things NASA does. People don't know. Currently, NASA operates over 100 different spacecraft. A lot of them around the Earth, a lot of them deeper in the solar system, some on the way to Mars, for example. But over a third of those spacecraft are actually Earth observing spacecraft. They're looking back at the Earth, trying to study the oceans, trying to study the atmosphere, trying to study the land, and see about the changes in the climate. So Earth science is a very big part. The next image on the upper middle part is a reminder that the first A in NASA stands for aeronautics. And so it is about flight. And so flying through the atmosphere, aircraft, flying faster, flying higher, flying more efficiently, reducing the emissions of aircraft. Currently today, aviation accounts for maybe just less than 10% of total emissions. But as more and more people fly, as you start to have drones potentially and unpiloted vehicles, that number could go up. So we want to make sure that aviation is environmentally friendly as well. And so things like biofuels or low emission fuels are things, or electric airplanes, like many drones are. Those are the type of things we are looking at when we talk about explore flight. The next image on the upper right, humans in space, of course, is what NASA is typically known for. And this is the International Space Station as an example. The International Space Station has been continuously occupied for 20 years now. So for all of you who are younger than 20 years old, which it looks like all of you are, I want you to think about this one point, and that is for your entire lifetime, there's always been at least one person who has not been living on the surface of this planet. So that's a pretty amazing accomplishment that we've always been able to have somebody up in space, up on the International Space Station. Now it's been different people. We typically don't have anybody on the station for more than a year. A year is kind of a long time. Most of the time, people are up there for 6 months at a time and they come back. But we've been rotating crew through for the past 20 years. And so the space station has been occupied internationally, not just US crew, but internationally for the last 20 years. On the lower left is what we call exploring moon to Mars. So NASA currently has a mission to return to the moon and then eventually onto Mars. And when we say return to the moon and onto Mars, we're talking about here with people. And so returning to the moon will be the first time we return to the moon since 50 years ago. And this time is not just a visit. This time is not just to stay for a few days and see that we can do it. This time is to actually try to learn how to live on another world where there are very big differences in how you have to live. The gravity level is different. The radiation levels are different. The temperature ranges are much different. On the moon, there really isn't an atmosphere. So how are you going to make sure you have air and water and food and all of those type of things? If we eventually do want to go to Mars and settle on Mars, we're going to have to learn how to not live on this surface of the planet. We've only learned how to live in low Earth orbit on the International Space Station. We have not learned how to live on another world for any length of time. The longest any Apollo astronauts spent on the moon were a matter of a few days. And so this is very different. And a trip to the moon takes a few days and a few days to come back. So you can do a round trip to the moon in a week or two. A trip to Mars right now takes about 7 months at the best time when Mars and Earth are aligned properly. And if you spend a couple months there and you come back, it's a shortest trip to Mars is going to be more than a year, 2 years. We've never had a system that had to go that far and stay that long on another world. So that's what our exploration from Moon to Mars is about. And then the bottom middle one is about science. And so much of what NASA does is driven by science. We're trying to understand the origins of the universe. We're trying to understand what's the future of the universe. We're trying to understand things about life. Where else does life exist in the universe? How did it begin? What is its future? We know life here on Earth, but we don't know its possibilities elsewhere. And so that is part of NASA's mission as well. And so biology is a very big part of it. I know many of you are interested in biology and bioengineering. There's a field that was some credit Ames for creating over 20 years ago called astrobiology. And it's the understanding of biological systems on other worlds and where else they might exist. And so it actually brings in fields like biology, but it also brings in fields like chemistry, geology, all those things you need to look at to really understand the origins of life and how life could begin on another world. And then finally, the image on the bottom right is that really representing that technology is also what drives much of what NASA does. NASA's missions are often first of a kind, usually one of a kind missions. It's not something we've built before. It's not something that we're building copies of. And so we need new technologies and new capabilities all the time. I know many of you are interested in computer science, and that's one of the key areas where we need advances in computer science. We need advances in autonomy and AI and robotics. We need, as we explore further out, humans are only going to be able to explore out a certain distance because of the challenges and the health issues and also just the time it takes to get somewhere. So as we explore further out, there's going to be more and more need for robotic assets that can do more. Right now, when we send a rover to Mars, it's still largely operated, teleoperated. We send commands up there every day, and then it moves a certain distance, and then we have to get that feedback, and then we do it again the next day. If you can imagine trying to operate a robot that way and how long it takes just to move it, say, a couple hundred yards and take a sample from a rock, it's very, very inefficient. And the time signal delay of just sending a signal to Mars and getting it back can be more than 20 minutes. And so it's very inefficient. And if we can get more autonomy and more AI and intelligence on board, machine intelligence on board a system, then it can do things itself. We can tell it, go take a sample of that rock. It's 100 yards away. It will know to avoid obstacles on the way. It will know where to position itself. It will know how to position the instrument. It'll know how to take the instrument, and then we'll get the measurement back and the science back in a day, as opposed to maybe a week that it takes to maneuver all of that by hand. So here, just a kind of an image of where all the NASA centers are located. There are 10 centers around the country, 3 of them here in California. Ames Research Center is the one here in Silicon Valley that I lead. Many of the other centers, some of them you may have heard of course. Johnson Space Center in Texas is where Mission Control is. Kennedy Space Center in Florida is where we launch most of our spacecraft from. And then there are other centers around the country. But this just gives you an idea of how NASA is distributed. The Mars missions are run by the Jet Propulsion Laboratory down in Southern California in Pasadena. And so this gives you kind of just a sense of where all the NASA centers are. The center that I run, Ames Research Center, it's actually been here quite a long time. It started in 1939. So we actually just celebrated our 80th birthday. And 80 years ago, NASA didn't exist. NASA didn't actually start until 1959. So 20 years before NASA was formed, we had this Ames Research Center, or what was called Ames Aeronautical Laboratory at that time. And in the early days, it was primarily about understanding aviation and flight and aircraft. And I'm going to get back to that because I think right now it's so exciting to be potentially interested, if you are, in space exploration, because we are almost at the same place we were for space that we were 100 years ago for aviation. And so I'll talk a little bit more about that. So throughout the history of Ames, we've done many things. This is sort of 80 years of pictures of things we've done. And I usually like to break this into 3 parts. So the first few decades, from say 1940 to 1960, we were, of course, before part of NASA, we were really about aviation and learning how to fly faster, how to fly higher, and how to fly through the atmosphere when you're trying to bring something back into the atmosphere without burning up. And so these are the type of things we did as a research back then, before my time as well. And then when we became part of NASA in the 60s, we actually got involved in space and involved in science missions, because NASA at that time was about sending probes to other planets, sending probes beyond the solar system. And so we became part of that while we continued our work in aviation. And then, of course, now we think about Silicon Valley and information sciences, computer science, and nanotechnology, and all these other cool fields that Silicon Valley represents, that didn't really come into being until the 80s or the 90s. And so for the last 3 or 4 decades, we also, because we're right in the heart of that, became part of Silicon Valley and really looked at how we could bring information sciences and information technology and artificial intelligence into enabling many of NASA's missions. So you just see some images there that help tell that story. So here's a picture of what the center looks like if you were to get a little bit higher up from 101 and peer in over the horizon a little bit. And so this is the picture of the center. You see a lot of facilities and buildings. The largest building or structure you see there is the largest wind tunnel in the world. You can put a full-size 737 airplane inside that wind tunnel, and you run air past it to study it and understand how the flow field works around an aircraft or any object. And then we have a lot of smaller tunnels. The smaller the tunnel, usually the higher the speed, because there's just a certain amount of energy you can put into it. And so if you want to run a tunnel at, say, supersonic speeds, faster than the speed of sound, then your test section gets smaller and smaller, and your models have to get smaller and smaller so that you can still apply that energy and test it. And then we have a very unique facility that's called the ArcJet. And this is a wind tunnel that we put high energy into it so that it actually simulates the conditions when a spacecraft enters the atmosphere. When a spacecraft enters or returns to Earth's atmosphere, the surface temperature gets to about 3,000 degrees. We're getting close to the temperature of the surface of the sun. And so that's how we have to, that's how much energy we have to manage and protect either the crew or the cargo from that spacecraft so that it doesn't burn up when it enters the atmosphere. There's some information on this chart. We have about 3,000 people who work on site. We host many students over the summertime in particular. Our total budget is about $1 billion US per year, and most of that is appropriated by Congress since we're part of the federal government. And then we have airfield and we have other assets on our property. This next image, and I only got a couple more charts left, but I just want to show you kind of some of the things we do. So these are 8 of what we call our core areas of research today. And I won't talk about all of these, but you may see some things that interest you. We do a lot of research in what we call air traffic management, studying how airplanes basically fly safely over our airspace. There are at normal times, of course, it's much less now due to COVID, but at normal times, there are thousands of airplanes in the air at any given time. At its peak in any given day, usually there are about 5,000 airplanes in the air. When we start to introduce drones and unpiloted vehicles and things like Amazon cargo delivery, when they want to do that, or personal air vehicles that might help us get past the traffic jams on the freeways, they're talking about potentially hundreds of thousands of aircraft in the air in the future. And so how do we manage all that? How do we make sure it all stays safe? So that's one area of key research for us. Entry systems is about the high temperature materials and the materials that we develop that help protect the spacecraft from entering the atmosphere. We do that not only for NASA spacecraft, but we also do that for the commercial companies. You're probably familiar or heard of SpaceX. So their Dragon spacecraft, for example, the heat shield is material that came from our center that we developed, and we transfer the technology to them. Our supercomputers, for those of you interested in computer science, right? We host the agency's primary supercomputing facilities. So we do a lot of work nowadays, unlike 30, 40 years ago or beyond, where you had to test everything. We now can simulate many things on computers and write codes that follow the laws of physics and basically use the mathematical equations that represent our understanding of physics. And so we can actually simulate airflow around a vehicle or inside a rocket engine or in many other ways, try to understand, or the structures, try to understand that and simulate them on a computer, which is much less expensive. And then eventually still have to test it because our computer models are only as good as the models are. And so if you make some bad assumptions in your computer models, you'll have some bad results. So at the end of the day, you still have to test things to make sure that it's real. What you're simulating in a computer is real and will work when you actually try to fly it. And so that's still, but we can do many more type of tests on the computers first, and then decide which ones are the ones that we think are the best ones to test in a facility, and do the more expensive building of a model and testing it in a facility. The intelligent adaptive systems is about artificial intelligence, is about autonomy, it's about robotics. And one thing I want all of you to think about is we all talk about how we can make things more intelligent for computers and increase the autonomy and the artificial intelligence. One of the biggest challenges is not about how to do that, but it's about how to make sure humans can work with those systems. So the psychology of how humans operate and work with autonomous systems is equally important. It's an area called human factors. And so we actually at NASA Ames have many people who are psychologists. They're not engineers or traditional scientists that you might think of, but they're psychologists and they're human factors experts because they understand how humans think and how humans work. And it's not so good if you create a great system and people don't know how to use it, or people assume it works one way when it's really doing something else. And so that's one of the biggest challenges in that whole world of making things smarter and more intelligent, is to also make sure you understand how people will work with those systems. And then on the lower left, we work on small spacecraft missions. And so all the way down to what we call CubeSats now, which you can build a spacecraft that's 10 centimeters by 10 centimeters and launch it into space, and potentially get real science out of it based on the instrumentation on board. The smartphones, the iPhones or Android phones that many of you have many of the same capabilities of a spacecraft. Right? They have accelerometers on them. They have gyroscopes on them. They have processors on them. They have cameras on them. Some of them might even have sensors on them that can look at pressure and tell you what altitude you're at. I mean, many of the spacecraft in the past had much less computing power and capability than everybody holds in their pocket these days with their phones. So just imagine how fast the technology has advanced. In the aerosciences world, we're still looking at how to improve the efficiency of aircraft, as I mentioned, and how to lower the sound, for example, when aircraft fly overhead. And in particular, we want to figure a way to get rid of the sonic boom that occurs when an aircraft flies supersonic. So if one day we can figure out how to reduce that boom into maybe a low rumble, then we could possibly fly commercial planes supersonic over land, which means a trip from San Francisco to the East Coast might only take 2 or 3 hours instead of 5 or 6 hours. And then the last two areas down here are about the science that I mentioned earlier, the life science and the astrobiology, which I already talked about, but also the space science and understanding where other planets might exist around other stars, and also understanding the formation of the universe and how that occurred over, we think, 14 billion years ago. And then we have the major facilities that we operate. And because the people are the most important part, and the people are the ones who do the work and understand what's going on, but they need facilities and laboratories to work in. So here are just some pictures. I won't go into these in detail, but we have wind tunnels, we have test facilities, we have simulators, we have computers. These are all facilities that help our researchers and our scientists and our engineers do their work. And then finally, I want to just leave, I can send these to you if you want to keep them, but here are some ideas of things that we have at the NASA website. The URL is up at the top there for STEM activities, particularly for students in 9th to 12th grade. And so NASA has a wealth of things on its website that you can go to look at that. And then I know some of you may be interested in internships. So NASA also has an internship website called interns.nasa.gov. Most of our interns are college level people, college level students or graduate students, but we also have high school interns, usually I think in their junior or senior years of high school, especially if they're local. But even nowadays with the pandemic and the fact that everything's being done virtually, we have some interns from farther away now that can participate. And so there are internship opportunities. I didn't start my internship until college, but we've hosted many interns at the high school level who then really, it helps them understand what it is they might be interested in and where their passions might lie. So I think that is my last slide. It is. So I'll stop sharing the screen And I know I probably took up a little bit more time on the presentation than was planned, but I'm happy to answer any questions you might have.
Alrighty, so that being said, we will start our Q&A session. So you guys can feel free to go ahead and type your questions in the chat. I will ask Dr. Tu. And here are the links that he was showing you all earlier, just so that way if you all want to check those out, you totally can. And that being said, we'll go ahead and ask the first question. So your model airplanes really did kind of give everyone a really cool look into kind of what you were doing when you were younger. So someone wanted to know, what type of materials did you build your planes out of?
Good question. Good question. So back in those days, nowadays, if you go to a model airplane or get a model airplane, most of the time it's styrofoam. Because it's lightweight but it can still be the proper shape. And of course, with an airplane, it's all about the shape and it's all about how much it weighs, and then it's all about how much power you have. So it's those three things together that make something fly. And so, but back in my day, the manufacturing and the styrofoam technology was not as good. So you actually had to build them more like a real airplane, which basically meant you had to have what they called balsa wood, which is very lightweight wood that would make the structure. And then you would have a sort of a plastic coating that would go around the frame that you build. And so, yeah, it would be a combination of balsa wood and plastic coating, I guess is the best way to describe how those planes were built back in those days.
Really cool. Okay, and then another one kind of about your earlier life. Someone wanted to know, what is the graduate and PhD experience like, and would you recommend going after higher education?
I certainly would recommend it, but it's not for everyone. It really depends what you want to do. It really depends what type of things you want to be doing. A lot of people actually benefit more from working for a while and then going back to school, because that really then helps them focus what their passion is on and what they like working on. You know, in my early career in college, I really thought I would be doing research most of my career. It obviously didn't turn out to be so. And I thought maybe after I did my research, had my career at NASA doing research and writing papers and doing experiments, that I might go teach at a university or teach somewhere. So I really did feel I was going to stay in the academic field, which then really does require a higher degree, master's or PhD to do that. But it turned out, of course, I took some opportunities that were presented to me, and I ended up going into management and leadership, and then ended up in my current position. So I actually haven't not done research for quite some time, but I still feel the advanced degree helped, because it also, not only do you become more of a technical expert in wherever you are getting your advanced degree in, doing a higher degree really teaches you to think in a different way, right? To be more creative, if you're going to get a PhD in any field, and that's not just the science and engineering fields, but also in the humanities and social sciences, you typically have to come up with something that hasn't been done before, right? It has to be new. It has to be, you can't repeat something that has been done before. You have to create something new. And so that causes you to learn how to think in a different way, how to explore things, how to make mistakes, because when you're trying to pursue something that hasn't been done before, there's no book written on exactly how to do it. You know, follow these steps in this recipe and you'll get to the answer. You're going to have to try things out. Some things will work, some things won't work. And so the whole trial and error and understanding and analyzing what worked and didn't work, and then continuing on. So I think there are cases where if you want to be a deep expert in your field, whatever your field is, you sometimes need to get an advanced degree, but there's also benefits to getting an advanced degree and just teaching you how to think differently and how to think more in that way. So yes, but then again, as I said before, it's not for everyone, and you really do have to be committed to doing that. It's a time commitment, as well as as a commitment of your passion and what you want to do. And so some people just want to get right to work and start making an impact immediately in whatever they're working on, and that's fine too. You can always choose to go back to school later or not.
Okay, so PhD work seems like a lot. So someone wanted to know, how did you balance your PhD work with your, I guess, actual career?
Yeah, that was, so for me it was fortunate because as I mentioned, I did get offered a position and took on a position in a research organization at NASA. And so that made it such that the work I was doing for NASA at work and getting paid for was often closely aligned with the research I needed to be doing for my PhD. And so that part made it that such that I didn't have to, it wasn't really double the work, right? It wasn't like I was working 8 hours a day and then I had to go figure out how to find time to do my schoolwork. Now, there was a period of time, and the reason it did take me longer is because I did, for my coursework, of course, I still had to do the classes and I still had to take the classes, take the exams and all those things. And that did not overlap with my with my work at NASA. So it took me a little bit longer to get through the coursework, but once I got into the mode of doing the research that was necessary for my PhD dissertation, that pretty much overlapped almost completely with my work at NASA.
Alrighty, so it seems like you kind of got your job at NASA through like your internship. So we had a couple of questions about how you got your NASA Ames internship and if it still offers internships today and how can high schoolers and other students get those internships.
Yeah, no, absolutely. So as I mentioned, I did not start in high school. I did not have that opportunity in high school. It was in college. I basically had been looking at opportunities and also had some connections with other students at Berkeley at the time who had internship opportunities. And so really what got me started was just talking to people, and initially being able to work essentially volunteer, right? I basically said, hey, I don't need, I'm not looking for a funded internship, which is sometimes harder to find in any organization because they have limited resources, but I'm willing to work just for the experience. And so I started with that, and spent, as I said, probably about 6 months doing that, part-time, because part of the time I was still in school. And so I would maybe on those days that I did not have classes, drive down to Ames and work with the researchers there. And so eventually then they offered me a paid internship as part of a program that NASA has, which NASA still has today, for interns. And many companies also have paid internship programs. So it just kind of led down that path. I initially volunteered, and then I did paid internship. And then after graduating from college, from the undergraduate, they offered me a permanent position, and an opportunity to do my graduate studies.
Okay, so kind of continuing on with the internship talk, we had some questions on what do you look for in internships and also what did you do your internship?
Okay. So I think what you want to look for, you mean from the perspective of a student looking for an internship? I think what you want to look for are those opportunities that might allow you to touch many different areas of an organization. I think for an early internship, it sometimes can be not the best to focus too narrowly and too quickly, right? Because two things. First of all, it may not be the only thing you're interested in, even though you think you're interested in it today. And second of all, it may turn out that there isn't a good fit between what you're interested in and what one organization or one part of the organization needs. And so I think to sort of improve your chances that you will actually make a connection and have a good fit with an organization, I think the more parts of the organization an internship might let you experience and let you touch and talk to people and network, the better it is. So I in general would look more for an internship that's sort of broader base if you can get it, and isn't so narrow in one specific area, because it may, like I said, turn out that you're not as interested as you thought in that area, or it may turn out that you weren't the best fit for that part of the organization. What was the second part of the question?
I believe it was what did you do during your internship?
What did I do? So, as I mentioned, since I got linked up with a research organization, I really did help them with the research. I learned to run the computer codes at that time. The field that I ended up doing my graduate work in is called computational fluid dynamics, which is basically using high-speed supercomputers to try to simulate the flow field around a vehicle or inside an engine or something of that nature. Anything that involves fluid physics, and of course, the air is a flow field as well, is a fluid as well. And so I learned how to operate the codes. I learned how to modify the codes. You know, I would try to do debugging sometimes, because a lot of times debugging is a very tedious task. And you just have to sit there and go through each line of code and run a part of the code and see if the input and the output match what you're expecting. And so in some ways, it can be grunt work, right? It just be time sink and difficult, but it's something that that certainly as an intern you would be willing to do and learn from, because you do learn from that experience. So I did that. I also helped with putting the final products together. As I mentioned, back in those days, we did have graphics computers and things like that, but nothing as capable as they are today. So in putting together a publication, you might have to print out a figure on a piece of paper, and you would cut it out and paste it into another piece of paper with the captions and the text underneath. So there's a lot of manual work involved in that, with copy machines and scissors and tape and all that kind of stuff to really make the final publication. So there's probably some equivalent to that today that people do. But there's always work I think an intern can do. And sometimes it may feel like the work that you're doing is sort of just a grunt work, but I think on the other hand, you're always learning when you're doing things like that, and just being in the environment will help you learn and help the folks who are hosting your internship learn about you and what you're capable of.
So I guess getting into NASA is a very popular topic. We had some questions about whether or not NASA conducts any competitions, I would presume for students, and also just questions about general recommendations and advice on how to get into NASA.
Yeah. Well, certainly, you mean competitions in terms of like projects, like robotic competitions and things like that? Is that the type of, I just want to make sure I'm answering the question properly.
I'm going to assume so.
Okay. Well, yeah, well, competition, I'll just say in general, competition is a very big part of how NASA operates, because it's a very big part of how the scientific community operates. The scientific community is about competing the best ideas. And so um, I'll I'll take it from sort of the basic level of just having some projects and maybe robotics competitions and design competitions. We do host many of those, often with universities or schools. We are, I think the previous speaker talked about the FIRST robotics program. We are a sponsor of that too. And we actually, Ames has some teams that participate in FIRST robotics. So that's one way to start learning and get into sort of a mode of a friendly competition about how to compete for the best ideas. But now take it all the way to how do we decide, how do we select a mission? For example, a mission was selected about a year ago now, which will take a octocopter, which is like a drone, and land it and fly it on one of Saturn's biggest moons, Titan. And so how was that mission selected? It's about $1 billion mission. That mission was selected through competition. So NASA puts out a competition to the broad community and says, you know, for up to this amount of money, give us your best ideas of what type of mission you want to fly and what type of science will you get out of it? What type of return will you get out of it? How will you do it technically? What will be the risks associated with it? So we do competitions at that level too. Some of the most exciting missions that you may have heard about were achieved through competition. And these missions are competed by, you know, usually there's a principal investigator. It's probably a university professor who will put a team together of engineers and scientists and then submit a proposal. And it goes through different phases of competition. Usually there's an initial, what we call a phase A competition, where maybe we will select 3 or 4 of them and give them a little bit more money to develop their idea more and spend a year. And then there's a down select to a phase B, and then ultimately a selection of a mission. So competition is much of how NASA does business, because in our in our society, in our world, we recognize that the competition can sometimes bring the best ideas forward.
Right. So here's a question that I actually wanted to know as well.
Mhm.
So someone wanted to know generally, what kind of work do you do as NASA Research Center Director?
Good question. Good question. So, a lot of the things I do nowadays is administrative, so may not be so exciting to many of you, especially those of you who are thinking of just starting out in the field. But it is actually quite enjoyable because as center director, I get a visibility into everything the center does. And I have to make decisions about at a very high level as to where we're going to invest our resources, what type of people we're going to hire, what type of fields are we going to emphasize because there's a future need for it within the agency or within NASA, what type of missions we're going to propose to. So I may have, for example, 5 scientists who each have a different mission. One wants to go to Venus, one wants to go to Enceladus, one wants to go to Mars with their idea and their spacecraft. And we, as a center, don't have enough resources to develop all of those ideas and put them forward to the competition that the agency will hold. And so we have to down select. We have to review those proposals and decide, okay, this one has the best chance of winning. This one is the most mature, or this one will bring back the most exciting science and is most responsive to the request for proposals. And so I do a lot of reviews. I have a leadership team, of course, that does that with me to decide which ones we will try to go forward with and compete for. A lot of the times where it's about managing the center's facilities and resources as well. And certainly during the last 9 months with COVID, it's been very different because I've had to manage a center where right now I only have about 25% of the workforce on site at the center, and most of the people are working remotely, just like I am from home. So it's a different way of managing and leading the people in the organization. So the thing that I like about what I'm doing now is it's never the same thing, right? It's always something different. I might be looking at an aeronautics project on one day, and the next day I'm looking at a project that involves going to Mars or going to one of the outer planets. And then the next day I might be worried about the animal care facility at our center and or some facility issue with one of the boilers in one of our major facilities. What I like about what I do now is it's a variety of things. It's never the same thing, and so from that perspective, it's challenging, and then also it's very rewarding because what you end up doing in leadership or management is not so much the work you personally do, but the work you enable the team and the organization to do. So I no longer, unlike my early days, as I described when I was an intern and trying to help a couple of people run their codes and publish the results, I now try to help 3,000 people in an organization achieve much bigger things because we're capable of that with the number of people that we have. And so it's just a different level of reward and recognition for what I try to do, because most of the work is done by the people who are actually doing the work.
So I think you mentioned something about how every day you're kind of doing something different. So there was a question kind of pertaining to that where they asked, what is something that surprised you during your job?
What surprises me? I guess it surprises me that sometimes there are always technical challenges that we did not envision, right? As good as we as people think we are in anticipating everything that can happen, everything that can go wrong, everything that should go right, we're just not that good at it. And that's why we need a team of people. And that's why we need a diverse team of people too. And so I'll touch on that point a little bit. A lot of people talk about what's the importance of diversity. Diversity is not just because it's representative of our society and our country, but it's also diversity represents the best answer, because just like we were talking earlier about competition, diversity brings in different ideas because everyone has a different experience. Everyone has a different way of looking at things. Everyone has different education and background. And when doing what we're doing as NASA, which every mission we do is a first of a kind or one of a kind mission, hasn't been done before. So we need the best ideas and the newest ideas and the things we haven't thought of in order to make that successful. So what still surprises me occasionally is that we think we've thought of everything, and then sometimes something comes up that we just didn't think of, and we have to address it. So that's also what I like about it. It surprises me, but it also what I like about the work is it's about problem solving, right? It's about finding a problem that you didn't anticipate, and then trying to figure out how to solve that. There was a question I saw in the registration form questions that said, what safeguards do you use to avoid making mistakes? You can't avoid making mistakes. What you can do is learn from the mistakes. Now, you of course try to minimize the mistakes, and you try to minimize the impact of a mistake. So when we're going to fly people, for example, in the air or into space, we obviously put in safeguards so that any mistakes that happen won't hopefully result in the loss of the mission or the loss of the crew or damage the health of people. We have not always been successful at that because it's a risky business, but we try to do that. But we also recognize that it's more important to learn from the mistake than to try to avoid all of them. I've often said that when somebody does research, you actually learn more from every mistake you made. You learn much more from every mistake you made than every success you had. Because when you have your successes, it pretty much is going exactly the way you planned and thought it would go, and you don't know what you missed. When you make a mistake, you actually learn something. And so that's probably what still surprises me is how many times things do come up that we haven't expected, and then we have to figure out how to solve it.
Alrighty, so this will go ahead and be our last question. We had a lot of really good questions, and I'm really sorry I couldn't get to all of them, but I have kept Dr. Tu here for a little bit longer than we told him to. So we're gonna go ahead and wrap up here. So what are some final words that you would like to say, or just final advice that you can give to students who are currently interested in kind of going into the engineering field?
Yeah. The advice I generally give is that, and it's because it was out of my own experience. I think it is good to have a plan, but you don't have to have one. So it's okay if you don't have a plan for where you want to be doing in a couple years, in 5 years, in 10 years in your career. But if you have a plan, that's great too. But in any case, whether you have a plan or don't have a plan, don't be so beholden to your plan that you skip or miss opportunities that come up that don't necessarily fit in what you originally thought you wanted to do. That happened in my career, as I mentioned. I originally thought I was going to do research my entire career. I originally thought maybe I'd do research and then I would go teach. But a management opportunity came up for me pretty early on at the lower levels in an organization, and then that grew into other opportunities. And then I ended up realizing I enjoyed it and I was fairly good at it, and that ended up where I am now in leading a center, which would have never been in my plan or even in my dreams when I started working for NASA. So I think it really does. My best advice to people who are starting out in their careers and looking at what they want to do next is you can not have a plan. That's okay. And just pursue your passion. You can have a plan, and that's great. But in either case, be okay with potentially deviating from that plan and taking some opportunities that come up. You could always get back to your plan, or you actually might find that the new path that the opportunity took you on is actually a better path for you.
Alrighty, well, thank you so much for speaking to us today, Dr. Tu, and taking the time out of your day.
My pleasure. It was the best part of the day. Enjoyed it.
We're honored. And of course, thank you, lovely audience, for sticking with us for that extra 8 minutes as we answered a couple of extra questions. Please don't forget, tomorrow's STEAM weekday is Art Day, and we'll be having a really cool graphic design workshop, completely interactive. So please feel free to go ahead and attend that one. Thank you all so much for attending, and have a wonderful evening.